Okay, so now what's the block level design method? I covered this topic. So more complex circuits can be built using block level methods. What's the block level method? In general, block level design method, opposed to the gate level design method, relies on algorithm or formulated circuit, which are obtained by decomposing the main problem to sub-problem recursively small enough to be. Okay, what method did we use now? We first formulate a problem. What we did then? Draw the truth table. But for some problem, if we draw the truth table, we cannot solve it. And that's a big problem. Why? I will explain the reason. I will explain the reason in the next slide. Okay, now, if we want to design a 4-bit adder, if we want to design a 4-bit adder, so 4-bit adder, so we have two inputs. The first input is X, other input is Y. How many bits for X? 4. How many bits for Y? 4. How many bits total? 8. And if we also have C in, how many total bits? 9. Now we have 9 inputs. We have 9 inputs. Now I will explain this with an example. So now if we say we want to design this 4-bit adder, any 4-bit adder. So if you want to design a 4-bit adder, so what should be the block diagram of the 4-bit adder? So this is a 4-bit adder. What should be the input? A3, A2, A1, A0. Because I want A plus B. A is a 4-bit data, B is a 4-bit data. What should be the other input? Yes, please help me. B3, B2, B1, and B0. And also we have another inputs. We call this as C in. This is the carry in. Okay, now this is A plus B. Now, if you look at, without looking at the output, if you look at the inputs, how many bits we need for the inputs? 9. How many combination? 5 and 12. And if we have a truth table of 5 and 12, you got it or not got it? So the thing that we want to show. So if you look, and you know what I'm saying here now, can you see here? So we can say in general block level design method. Now we are using the previous method was the Karnaugh map method. The Karnaugh map method is only suitable for like a variable of 4, 5, or 6, maximum 6. More than 6, it's very difficult to solve it. Karnaugh. So if some problem cannot be used using Karnaugh method, so we should use the block level design method. And I'll explain the block level design method next. So block level design method is opposed to the gate level design. So the Karnaugh map is the gate level design. And now we are going to discuss the block level design method. Got it? And this block level design method, we are using it for the adder. So can you see here the 4-bit adder? Okay. Now, if we want to formulate a 4-bit adder, so how can we create a 4-bit adder? So this 4-bit adder can be created using 4 1-bit adders. How? 1-bit full adder or half adders? Full adder. Full adder is 1-bit adder. So assume that now we have. So if you want to do any addition, let's assume we have some addition. So we have A0. What is A0? Then what? B0. Then what? A1, B1. Then A2, B2. Then A3 and B3. And now we have C in from here. So we add C in A0 plus B0. It's a 1-bit adder. Half adder or full adder? Full adder. Because in half adder we don't have C in. Okay, now if we add A0 and B0 and C in, we get some S0. S0 is some 0. But it will create a carry out, and this carry out will become what? Carry in for the next stage. So we again need C1 here. So now how do we design a 4-bit adder? We have the stage 0, then stage 1, then stage 2, and then stage 3. Got it or not got it? Okay, how do we design? So to add 4-bit binary numbers A and B, so we can say we have X0, Y0, X1, Y1, X2, Y2, X3, Y3. And can you see from here, what is carry in now? 0. This is the carry in. So how many inputs are there? X0, Y0 and scene. Remember, we design 1-bit full adder. Please revise your that topic. Okay, now we have what? S0. S0 is sum. Now this C1 is what? Carry out from which stage? The first stage. It will become as carry in for what? Next stage. So can you see here? What are the inputs? 1, 2, 3. What are the inputs? C1. What are the outputs? So every full adder have how many inputs? 3 inputs. How many outputs from a 1-bit adder? 2. Any question? So this method is easy or not? Okay, now assume we want to design a 32-bit adder. How many combination? 2 is for 32. If we want to design a 16-bit adder, how many combination? 2 is for 16. 65,536. Are you able to draw a Karnaugh map of 65,536 or not? No. So now answer me. So should we use Karnaugh map every time? No. So it depends on the scenario. It depends on the application. It depends on the user specification. And on the user specification, we need to know which method should we use. So Karnaugh map is only and only tractable or manageable when the number of variables are how many? Maximum 6. If it's more than 6, it becomes intractable. There is also another method, Kuhn-Max-Loxi method. That's another thing, but I'm not going to detail it. It's a very advanced topic. Okay, so now if you want to design, in this example, we are designing, what is the size of the adder now in this example? 4-bit. So if you want to design an 8-bit adder, how many? We need 8 full adders. The same thing like a train. You have different compartments on the train. You want more compartment. You add just one compartment, one compartment. So now we need one full adder. And if you look at this one full adder, remember. So this one full adder. Remember this one full adder. If you want to implement it using half adder, so this one full adder contains how many half adders? 2 half adders and 1 OR gate. So this. And there are different implementation of this full adder. This is the black box. This is the black box. So the implementation of the full adder, this full adder can be implemented using the SOP expression. This full adder can be implemented using the POS expression. This full adder can be implemented using the mixed gate approach. Got it? And this full adder can be implemented using 2 half adders and OR gate. So these are different implementation of the full adder. But this is a black box. Do you see something in the black box? No. So this method is called, which method is called? Block level design approach. And block level design approach, we will, in the following lecture, we will study block level design approach. We will also study Karnaugh map. So we need to think, should we use the block level or the Karnaugh map? It varies from scenario to scenario. Okay, now if you have this thing, so now C1, C2, C3 and C4, what are these? Carry out or carry in? They can be also carry out and carry in. So C1 is the carry out from this stage and carry in at this stage. This one is carry out from this stage and carry in for the next. Any question? Should we proceed? Okay. No, this is the example how it works. So if you say, so now you want to design a 4-bit adder, how many possible combination? Just for 9. Yes. So actually, if we okay, now another question. Just formulate. We want to formulate a problem. If we want to have an n-bit adder, how many possible combination do we have? 2 is for 2n plus 1. Because 4 multiplied by 2 is what? 8 plus 1. Okay, 3-bit adder. 3 multiplied by 2, 6 plus 1, 7. So if we have an n-bit adder, so we say 2 to the power 2n plus 1. What is n here? 4. 2n, 2 multiplied by 4 plus 1. So yes, please.
Can you do like a truth table support for each one?
If you can do it, I can.
No, like for the 4-bit support truth table and for the second one support.
You can do that, but try it and try to solve this if you can do it. So this is your homework. This is your homework. And then please, you do it. You did. Okay, now the problem is, there are some questions in your mind. You try this on your own and then you'll learn something. And maybe you derive the same expression that we had in there. So there are 5 outputs. So now if you look at here, 4-bit parallel adder. So now, until that, so now we have a 4-bit parallel adder. What is Ci plus 1? It is the MSB. What is Si? The LSB. Remember, we did some full adder. Remember the full adder or not? We draw the truth table again, and everyone will, just forgot all these things. Now, if you have any full adder, so we have AI. AI is what? Input or output? AI, input or output? Input. BI, input, and then CI, input. What should be the output? SI. Why we call this Ci plus 1? Carry in for the next stage. So we have how many combinations? 0, 0, 0, 0, 0, 1. So I call this as Ci plus 1, Ci plus 1, and Si, if you remember, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Got it? Okay, now 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1. How did I do? 1 plus 1 plus 1, 3, 1, 1. 1 plus 1, 2, 1, 0. Carry is the MSB and SI is the. Got it? So now this is how do you derive the truth table. This is the truth table for what? Full adder. This is the truth table of full adder. And then you can have a Karnaugh map for Ci plus 1, Karnaugh map for Si. You can derive the SOP expression by putting 1. If you want to derive the POS expression, we invert that. There are 2 methods we did it. You can derive the SOP. Then you can use a full get mixed get approach. We did study this in thing. So now if you look at here, Ci plus 1 is the carry out and Si is the sum. And now we derived this expression in your previous lectures. Okay, Ci plus 1 is Xi, Yi, and AND gate, and this is exclusive OR gate. Which approach is this? Mixed gate approach. Remember the mixed gate approach. Okay, so now we have the 4-bit adder. Okay, now how do we cascade the 4-bit adder? So we can say C in first stage or second stage? First. What are the inputs? X0, Y0. What are the outputs? C1 and S0. So this C1 is actually I plus 1. What is I? 0. I0 because Ci plus 1. What is I? I is equal to 1. And that's the reason that we have C2. Ci plus 1. C2 is actually Ci plus 1. I is 1. Okay, now if you look at here, X2, Y2, what is I? 2. This is Ci plus 1. Again, another stage, another stage. And you can replicate this until an AND gate. This is called as ripple carry adder. Ripple. It's rippling through from stage 1 to stage 2, stage 3. So something like this. So I can say C in, I give you the inputs, and then you give it to the stage 1, then stage 2, and then you give it to the stage 3, then it gives to third 4, and it can replicate. This is called as ripple carry adder. It's rippling. It's rippling from one stage to another stage, and so forth, so on. It goes on. If you look at the observation, so there is something blue thingy and the red thingy. What is blue thingy? What is the red thingy? And what is the green thingy? Blue are the inputs. The red thingy, the intermediate signals within the block, and the green thingy, output. So if you look at here, so the blue thingy, the blue thing is the block. So if you look at the complete, now this is a complete block diagram. This is the complete block diagram of a 4-bit adder with the input of X0, X1, X2, and X3 with the input of Y0, Y1, Y2, and Y3. C in is the input, C out is the output. And within this inside, these are the intermediate signals. It does not appear to the output. Got it or not got it? Question. And the thing, now we can also have an analogy of a programming in a programming. If you look at the functions within C, C++, we have some variables within the functions, inside the function. Are they visible outside to the function? No. What are the signals which are not visible to outside? C1, C2, and C3 are the signals which are not visible outside. And what are the signals which are visible to the outside? C out, which is actually C4, which is visible, and S0, S1, S2, and S3. These are the input. So if you think of a function in C, C++, so these are the outputs arguments, these are the input argument, this is the output argument, and these are the variables within the function, just like an analogy. That's not good, but this is like how it works. Any question? Should we proceed? Should we proceed? Okay. Now, so if you say, okay, now we want to have 32-bit triple carry adder, how can we design it? How many stages? 32. 32 stages, and 64-bit adder, similarly 64-bit. So now this method is called as a triple carry adder. And each adder, if you look at each adder, inside this adder, how many gates are there? Remember? There may be some exclusive OR gates. So if you look at here, now look at this slide. Can you see here? Now look at Ci plus 1. We need one exclusive OR gate because exclusive OR gate is only 2. One exclusive OR gate for this, 2 exclusive OR gates. Okay, and then Si, and you know the same exclusive OR gate. Now this is logic sharing. We need an AND gate here, and then we need an AND gate here, and then we need an OR gate. How to derive this expression? So if you see, so now I'm now only drawing this circuit for only 1-bit adder. I'm drawing the circuit for 1-bit adder, and please look at here. Let's see. Now, if you look at here, what is Si? So now we are using 2 exclusive OR gates. What is the input? Xi, Yi, and Ci. Got it? How many exclusive OR gates? 2. What is output? Si. Okay. Now this input is now shared. Can you see? Si exclusive OR, Yi, and then Ci. So Ci is here. Got it? Ci. And then Ci, this is OR. What is output? Help me. What is output? Si. So this is what is this? So Ci and Xi, Yi, this is the first input. So this is done here. Now what is the second input? Xi and Yi. So now you have Xi, and then what? Yi, and then what? Got it? Okay. So if you look at this, any 1-bit adder, how many exclusive OR gates? 2 exclusive OR gates. How many AND gates? 2 AND gates. 2 exclusive OR gates. 2 exclusive AND. So how many total number of gates do we require in an n-bit adder? So if you have an n-bit adder, n-bit adder, and we want to have a ripple carry adder, so how many total adder do we need? So we need 2 n exclusive OR gates. 1 plus 1, 2. How many AND gates? 2n. AND gates. And how many OR gates? N. Any question? Any question? Should we proceed? Interesting or not interesting? Or boring? I'm too boring, you know, you don't like me. Okay, so now this is how it works. So now it is cascading 4-bit adder. So now if you look at here, so now this is a full adder block diagram, and now this is the complete input of this block diagram. So we copy this and then we paste this, and this output, this is Si, and sorry, this is Ci, not Si. This is Ci. This output Ci will become the Ci for the next stage. So this is I plus 1. So now we have this gates. So now we have this gates here, and gates here, and this is how. Okay, now if you look at the critical path, so how many gates are in the critical path? So now this is the critical path. Can you see here? So this will become the critical path. It will become again for the next stage. So now this will become the critical path. Okay, critical path is the longest path. So now this is the 32-bit ripple carry adder. Now we want to design. Okay, now we solved one problem. Remember, we solved one problem. Now we are using the block level design approach, not the gate level. We designed the BCD to XS3 code converter. Remember last time? What did we do? Draw the truth table, logic minimization, But we can also design a BCD to XX3 code converter using an adder. How? Let's see. Jet add 3. So can you see here? So now if you see, now this is a BCD code. How many bits? 4 bits. And then what we add? Why 0011? Because 3. Because anything added with BCD, what should we see in? 0. What should we see out? Unused. XX3 code. Got it? Okay, now think. Now we can solve this. Okay, can we solve this problem using another technique? The same block diagram, but using a different combination, and we give you the BCD code. A different solution. Think of a different solution. Anyone? Think of a different solution. So can you see here? Yeah, this is very important. This is very important. Okay. Now assume that what is XX3? How can we calculate XX3? XX3 is equal to what? BCD plus what? Plus 3 plus 0, which is seen. So can we write it something like this? XX3 is equal to BCD plus 2 plus 1. Okay, so now the same thing. If Cin is 1, if Cin is 1 and 0010, we achieve the same objective or not? So there are different solutions to the same problem. So now this method is called, which method? Which method is this called? Block level design method. So I may also ask you this question: design a BCD to. Okay, now there may be a question of theory. Okay, design. How can you design a BCD to XX3 method? What are different methods? And then you write, okay, method number 1, method number 2, method number 3. This is called as the logical explanation. This is called as the analytical. Like how do you solve it? Okay, how can we solve? Yes, please. Can you answer me? How can we solve? We want to have a BCD to XX3 code converter. What is method number 1? BCD plus 3. But what is the other method? Draw the truth table, Carnap map, logic sharing, logic minimization, and then logic verification. That's the step number 1. And now this is step number 2. You have the adder. Yes, please. What is 2 plus 1? Yes. So, but if you say, now in this case, now this is your Cin. In this case, Cin is what? 0. In the other case, 1. So if Cin is 1, so we can make it 0, 0, 1, 0. So 2 plus 1, 3, 3 again. You got it or not got it now? That's the thing, that how do we solve it? So now this is another way to solve this problem. So now arithmetic, now there are parallel methods. Okay, we can do this in our next lecture. But now have some pen and pencil.